Today's focus will be on the basics of waves. There are two overall kinds of motion. Okay, one is linear motion, and that's what we just learned about. It's when you go from point A to point B. That's when you measure the speed, things like that. Okay, and it can go forward and you can go backwards. Okay, but you're going from a distance from A to B. The other type of motion that you get is a simple harmonic motion, and what that is it's where it repeats its motion over and over again. So a swing set or a pendulum. Pendulum is basically a swing, if you want to think of it that way. But a swing set, if you go back and forth, back and forth, back and forth. That is a harmonic motion. If you ever have seen like a hypnotist with the watch and it goes back and forth, back and forth, that's a simple harmonic motion where they repeat itself over and over and over again. All right. So regardless of it, a simple harmonic motion is called an oscillation, whether it is moving up and down like this, up and down, up and down, up and down, or back and forth, or side to side. Okay, all of those are harmonic motions. It doesn't matter the direction as long as you keep going back and forth, back and forth, and back and forth. And actually, if you graph it, what you end up getting is a wave. Okay, and we're going to be focusing on the waves. Okay, so what this does is if you look at this little spring, if it were to go back and forth, or up and down, sorry, up and down, and it had a little pen coming out of it, like out of the front, and it was able to ink like or draw on this paper that is moving in this direction. Okay, so this paper is constantly moving towards the right. What would happen is you would end up with a graph that looks like a wave. Okay, so that's what, if you graph a simple harmonic motion, it forms a wave. Okay, of these oscillations. So what are some other examples of things that create the simple harmonic motion? Well, we've got a pendulum. That's this thing. Okay, it's going back and forth. It's where it's weighted on the bottom and it moves back and forth, just exactly like the watch of a hypnotist. Planet orbiting the sun. So, boop, 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 right? Your heart beating, and then a phone vibrating. All of those are forms of simple harmonic motion. So as we did on the other page with the spring, if we graphed it, what would happen is you would always end up with a wave looking thing like this. Okay, so what this graph shows right here is that we have a tire, and once again, it's like a swing, back and forth, back and forth. Displacement, so what we're doing is we are graphing how far from the origin is it, okay, how far from it started. So this is the starting point right here, okay, then we move to the right. So what we're doing is we are going away from the origin, and then the swing moves back to the origin. So we've got this shape, and then now it moves to the other side towards the left, and now so we graph it this way. All right, so notice that it is forming the wave, and then if we let the next slide come where it goes back to the origin, it would look like this. Obviously a much better swing looking, or a much better wave looking thing that's more uniform, but you get the idea. All right, parts of a wave. So there are major parts of the wave that you're going to absolutely need to label. So we've got like this type of a thing. So we've got the crest. Okay, the crest is the top part of the wave. So I'm going to label this wave, and this is known as the crest. There are multiple crests on here. These are both crests, right? Okay, you've got the trough, which is the bottom of a wave. What I always think of is I think of a pig trough. Okay, a pig trough is where they eat out of. It kind of looks like this, okay, and then you put the scraps in here, and that's a pig trough. But it's the bottom. It kind of forms that same shape. You have the amplitude. The amplitude is from the crest to the origin, okay, or the trough to the origin. So what is an origin? Let's go for that first. That's the original placement, so where it starts. Okay, so here's an origin as far as the distance goes. Okay, now what you're going to do is you have to measure, and I didn't make it uniform at all in my wave. So actually I'm going to move my origin up a little bit. I'm going to erase this part right here. Didn't want to erase the wave. We'll say that's a trough. Okay, obviously really bad. But what the amplitude is if you take the distance between the origin and the crest, this is the amplitude, or the origin and the trough. This is the amplitude. So basically, if you look at your entire wave, okay, the height of it, this is not the amplitude where you do the whole thing. It is basically half of it, okay? And then a wavelength, if you were to do a wavelength is either crest to crest. That's a wavelength. We have trough to trough, that is a wavelength, or you can have origin to kind of like origin in the middle. So 1 to 2. So that would be a wavelength too. It's where it completes a complete cycle of either going a full crest and trough, or half a trough, a full crest, and then half a trough. So it adds up to be a full trough and a full crest, basically. And then the last one is medium. The medium is the material or substance that the wave is traveling through. That could be like water when you see water waves. That could be air when you see sound waves. All these things that where it travels through is going to be your medium. All right, so let's label these parts. So the first one, once again, is the origin. That's where your starting point is. Then you've got your crest. You have your trough, which is the bottom. You have your wavelength, which is peak to peak, or which is crest to crest, or you could have said trough to trough, or you could have gone from here to here, origin to basically origin, but where you get a full one. Okay, and then amplitude is half of the full from crest to trough. It's half of that distance, so it's really the origin to crest or origin to trough. All right, let's compare these guys. So you are going to have to be talking about frequency and wavelength a lot, okay, and amplitude. So amplitude, if you look at this measurement and you look at this measurement, to me it kind of looks the same. I'd have to get out a ruler, but the amplitude to this one looks pretty similar. Then if we're looking at wavelengths, okay, if I look at this wavelength from here to here, which we're going to do crest to crest, crest to crest, what do you know about the wavelength if we go from A to B? What you should notice is that it gets more squished, which means your wavelength is shorter. Okay, and then you have wavelength from here, which is trough to trough, and you're measuring it from trough to trough here. And what do you notice? It also gets shorter. So it doesn't matter whether you're measuring from crest to crest or trough to trough, your wavelength will either get larger or shorter depending on the scenario, but it will be consistent. Then we talk about high and low frequency. What does that mean? Frequency is how often you see a complete wave in a given amount of time. So pretend that this whole thing is 1 second, okay? So if this whole graph is 1 second, so from point A, this part, to point B, that is actually a measurement of time. We used an axis, and this is time, and let's say it's 1 second. Okay, if you think of frequency, just think of how frequent you see it. So which one do you see, if this is also a second, which one do you see more frequently? Well, you see the bottom one more frequency, therefore it has a higher frequency, is what we say. You see it more frequent, it has a higher frequency. The top one has a lower frequency, we do not see it as often. Okay, so measuring time. So I did talk about time. Time is extremely important when you're talking about waves. There are two ways that you can measure it. One is period and the other is frequency. Period is the measure amount of time it takes for one whole wave to pass. Okay, so a period of time is how long does it take to go from here to here or from here to here. Okay, so let's pretend that we had a graph. Okay, the period, this would be, let's say, my time. Okay, I'm on the same one, I'm just doing two different waves. From here to here, let's say, is 1 second, which means from here to here would be about 1 second. So how long does it take? Well, it takes 1 second for this first one, for letter A to go, but I would say it takes about a third or a quarter of a second for wave B to go. So its period would be the amount of time it takes for the wave. So it would be either 1 second or a quarter of a second. Frequency is how many waves you see in a whole amount of time. So in that case, we have this, okay, and we have a wave. So let's say this is a second. Okay, we're going to say once again, it's just comparison time. So this is 1 second. And then we also have 1 second. Okay, I'm trying to make it even as far as distance goes. It's not, it's a little, the second one is a little bit longer, but let's pretend this is wave A and now I have wave B. Okay, so this is wave B. All right, so number of waves. For A, I would say I saw 1 wave for a second, or 1 oscillation. And B, I would say I saw 1, 2, 3 waves per second. Okay, so obviously B I have as a higher frequency because I see it more often. All right, so these are the different formulas, and we will be giving you these, but I want you to understand that they are inversely related. So as your period increases, your frequency decreases. And you are going to have to use these, but period, it's a weird symbol. It's capital T. Once again, you won't have to memorize these. We'll give you them, but you do have to be able to apply them. And F, like a that F is little cursive ES is F is actually frequency. Okay, and frequency is number of oscillations, or another way to look at it is a number of waves for over time. And it equals 1 over capital T, which is time, or you have 1 for period, you have 1 over the frequency, which is 1 over F. And they are inversely related. If you remember back to graphs, what that would look like is something like that. So as one increased, the other decreased at a disproportional rate. All right, so let's do some calculation problems using these formulas. So this first one is calculate the frequency with a period of 4 seconds. So I know I need to solve for frequency, and I'm going to either do number of oscillations over time or 1 over t, which is my period. So what I'm going to do is I'm going to use this second formula because I don't know the number of oscillations. It doesn't give me that, but it does give me my period. So what I'm going to do is I'm going to say frequency equals 1 over capital T, which is equal to 1 over 4 seconds, which equals 0.25. And then we'll talk about units in a little bit. Okay, and then you count waves. Okay, so then you count 3 waves past you in 1 second. What is the period of one of these waves? Okay, so for this guy, what we're going to do is we're going to figure out this, which is frequency, or which is period. We're going to use this one. Okay, but I tell you 3 waves in 1 second. Yikes, I don't directly tell you the frequency. So this one's a little tricky because in order, first what you're going to have to do is you're going to actually have to figure out the frequency and then go to the next problem. So this is a 2-stepper. So what you're first going to have to do is figure out my frequency. My frequency equals number of oscillations, which is waves. So I'm going to write 3 waves divided by 1 second because that's my time. So it is 3. Okay, then what is the period? So then I have to figure out the period. The period is 1 over F is equal to my period. So I'm going to have to take now 1 over 3. So we get 0.33. All right. Wavelength and frequency are also inversely related. What that means is that one goes up, the other goes down disproportionately. That means that I see if it's a longer wavelength, it is a longer wavelength. Okay, it is a less frequent, it has a lower frequency. So I don't see it as often as something that has a shorter wavelength. It has a higher frequency. So different colors of light have different frequencies, which means they have a different wavelength. Okay, they have a different wavelength. So that's how actually we can tell different colors, is we can base it off of their wavelength, we can base it off of their frequency. Okay, there's a wide variety of frequencies, and the whole range of frequencies is known as a spectrum. So going from point A to point B with all of the frequencies and wavelengths in between, that is what we call it as our spectrum. And we call it like an electromagnetic spectrum. Okay, so that if you notice of all our waves, that's called an electromagnetic spectrum. It's the whole thing from the largest wave to the smallest waves. All right, so let's try to answer these questions. Which type of wave has the longest wavelength? So we're looking for the longest wavelength, and if you look at down here, it tells you that the longer wavelength, or you could look at the image, which is what I do. These guys look longer, so you would be talking about radio waves. What has the shortest wavelength? Well, that'd be the opposite. So you look on this end, and those look really close together. So that means that they're very short, and these would be gamma. What type of wave is the least frequent? So meaning I don't see it the most. That would be, once again, radio waves. Notice that they are opposite. And then the most frequent would be your gamma. What I want you to note about this is that we also have a visible spectrum in this, guys. This is the visible light. This is where we see color. So this is the only area of the spectrum, of the electromagnetic spectrum, which is the things that travel in waves, that we can actually see. All right, so this is the only area. We cannot see radio or microwaves. We cannot see X-rays or gamma rays. We can only see this little itty bitty area of wavelength. That's all our eyes can detect of visible light. All right, so let's analyze the chart of this. Okay, so we're going to be comparing our wavelengths. We're comparing our frequencies. So everybody look at, I would compare A to B, so the top to the bottom. And when you look at this, what I want you to understand is that this has a long wavelength at the top. Okay, this is your long wavelength. This is your shorter wavelength. You have a lower frequency, meaning you don't see it as often. You have a higher frequency, which means you see it more often. And then let's talk about energy. Okay, if we're to look at these two, and this usually doesn't cause a lot of struggle for students. If we look at these two, which one looks like has more energy associated with it? I would definitely say B does, because if you look at it, it's like, right? Whereas A is like, right? So which one has more energy associated with it? Obviously, the thing that goes up and down so much more often than something that takes more of a rolling type of thing. So the low energy always is associated with a long wavelength and a low frequency. High energy is associated with a very short wavelength and a high frequency. I typically like to draw two very extreme waves when I'm trying to compare wavelength and frequency. I draw a very long wave and then I draw a very short wave. And then I try to figure out, okay, which one has the low frequency, which one has the low energy, which one has high frequency, high energy, long wave things like that. All right, so there are quite a few variables that you're going to have to know. And V is going to be your speed of wave, and that is measured in meters per second. This guy is a newbie. That represents your wavelength. It is known as lambda. A lot of times in sciences, what we do is we use, and math, we use these Greek symbols. This is the Greek symbol of, or Greek letter of lambda. And so we use that as a wavelength. If you do like an upside down Y, that works perfectly. It's wavelength. So what do we measure length in? That would be meters. So these kind of make sense once you know what the variable is. And we're back to frequency, which we've talked about a little bit and did some calculation. Frequency is actually measured in hertz, okay? Hz, seconds to the negative first, or 1/seconds. All of these guys right here, okay, that I'm circling, all of those units, hertz, seconds to negative first, 1/seconds, these are all the same exact unit. Okay, so it's saying the exact same thing, it's just how you want to write it. Typically in this class, we will be using frequency as in hertz, okay? Period, by the way, is seconds. Okay, so that would be your unit for period. All of these will be given to you. You do not have to memorize them, and you don't have to, all you have to do is be able to match up this unit to that, knowing its frequency, and this is meters going to wavelength, and that will all be given to you also. So you're not going to have to memorize any of these per se. You're just going to have to be able to kind of be familiar with them, so it makes it a little bit easier for you to identify them. All right, here are the different formulas that we are going to be using. Notice that we are bringing out the triangle a lot, okay? And once again, you will be given these. And so what I want you guys to do is look at them. What this says is the first one is it's saying velocity, which is speed, is equal velocity divided by frequency, which is F, is equal to your wavelength, okay? Then this guy is saying wavelength is divided by your speed is equal to your period, okay? And then distance divided by speed equals your time, okay? Or if you want to look at it the other way, if we're solving for velocity or speed, it's going to be frequency times my lambda, which is my wavelength. Or if I'm trying to solve for velocity here, it's going to be my wavelength divided by my period. If I'm trying to solve for speed here, it's going to be distance divided by time. We will be doing a lot of practice problems with this, and these will always be given to you. You just have to figure out what variables you have, and therefore which ones are you going to be using. So let's say I give you my frequency is something, my wavelength is something, and I'm asking you what is its speed or velocity. Which one would we do? So what you want to do is look for something with frequency and wavelength in it, which would not be this last one. Oh, I see wavelength, but I don't see frequency. I see period, so that would not work. And then I'm going to go to the first guy. Oh my gosh, I have frequency, I have my wavelength, and I'm asking for this, so therefore I would be using this formula. Okay, so now it's going to get a little bit trickier for this because you're going to have to figure out of which formula are you going to use to solve the problem. Okay, but once again, there's no memorization that you need to do. All you need to do is be able to apply the work into these problems or into these formulas. All right, have a great day.